So Daisy decided to wake up and stretch. And here she is. She's really old. She's old. And you will have rotten teeth. Oh, hi, buddy. And then Archie's jealous of all the attention. I know. So anyway, here's my doggos. They're just saying hi. Oh, it's okay. I know you're freaking out. You're like, I'm too high. I'm gonna fall. She's kind of blind, so she can't really see much. Oh, she's like, don't take my attention. Grr. Okay, have fun playing. Don't hurt each other. Okay, so this video, let me switch cameras. This video here, I want to finish up the emission spectra notes. We got most of the way done. We talked about absorption, emission, all the different drops and how 4 of those drops we humans can see. And then down here, there was just this little space and a hydrogen and a helium. I'm going to zoom in a lot. It's going to probably make a lot of terrible crunchy noises on the screen. So actually, let me turn off the mic for a second and then I'll zoom in. Okay, and we're back. So here, I'm zoomed into those 2 little pictures at the end. This one is hydrogen. You can tell because it has 1 proton and 1 electron. Helium down here has 2 protons. It actually has some neutrons in there as well. But the important part is to focus on the number of electrons and also the ring spacing. So here's hydrogen's electron, and here are the 2 electrons for helium. Now, even if I were to get rid of, let's say I got rid of this one. Whoop, goodbye. Then some students might say, well, if we're not worried about the nucleus, and we're not worried about that 1 electron, wouldn't hydrogen and helium without an electron be the same exact thing? And the answer is no. Even though, like, you're like, but if the nucleus is irrelevant and you took out that electron, then don't they both just have an electron? Yes, but look at the rings. Because in a hydrogen, here's ring 1, here's ring 2, here's ring 3. Notice the spacing. There's teeny spacing between those 2. But that's not what's happening here. Like, look, this first ring is way closer for helium than it is for hydrogen. The ring spacing matters. The ring spacing matters because it's the distance between the rings that was making it give us the different stripes. Different stripe patterns happens because of different ring distances. Normally, when you go up and down a regular set of stairs at your house, you've got stair 1, stair 2, stair 3, stair 4. That is not at all how it works for atoms. Atoms, you might have, step, let's see, step 1, step 2, step 3, step 4, step 5. This could be the ring system for 1 atom. And then the next one could be here and here and here and here. So when I say an electron is jumping from ring 2 to ring 1, that's a very different jump. here versus here. The distance corresponds to your barcode. So even though you could try and make these two as similar as possible, the fact that their rings are different is going to make different barcodes. So hydrogen has a barcode of 1, 2, 3, 4 that we can see. Red, light blue, dark blue, purple. Helium, I'm not going to color it, has, I will darken it. Helium has 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm not sure if this is an exactly accurate image, but helium does have much, much more than hydrogen. So up here in the blank space that we left, I'm going to say, oh, this is kind of complicated to fit into such a tiny space, but that's okay. We're going to say each element has its own unique barcode, aka bright line emission spectra, because two reasons. You might get some differences in complexity due to the different amounts of electrons that are falling. If you are an atom that has lots and lots of electrons, that's going to complicate a ton of it. But also, even if you were to have the same number of electrons, like I just showed here, we could remove this and get the same number, but your barcode won't be the same because every element's ring system is at different heights that it's falling, or maybe I'll say distances. The distances correspond to the stripes. So the stripes are different because the ring systems are different. So that is the entirety of this page here for emission spectra. But what I'm going to show you next are some videos of other elements and what these look like, not in cartoon form, but actual photography form. So what's happening in this first video is similar to the setup in the notebook. The guy has a tube of an element, and he's putting electricity into it. It's shining, and then he's using not a prism, but a little diffraction gradient. It's a little piece of plastic to show the separation of the colors. So screen share. Full screen. So here I'm paused in the middle of the video, and I'm going to turn the sound off on him. But what we've got in the background is the tube. It's a glass tube that they pump in the element into, usually in its gas form. Ooh, look, now you can't see. And then over, I feel like a TikToker. Over here, we've got, he's holding a little piece of plastic, and it shows those stripes. Those stripes combined are what your eye sees as this color. So this color are these stripes coming together. So I'll play the video. I'll minimize myself so I'm not taking up the whole screen here. But let's see. The light from hydrogen consisted of only a few specific wavelengths. We've studied hydrogen a lot. So here's his diffraction gradient passing through hydrogen. So there's supposed to be 4. It just was a little bit blended in his video. Here's helium for comparison. Look at how much more complex it is. You've got double striping happening. Helium showed a different set of specific wavelengths. Astronomers use these spectral fingerprints slash barcodes to figure out what element is what. So just like stores can scan the barcode, we can use these striping patterns to see what elements, or in this case, compounds, are present. The more and more complicated the element or the compound, the more stripes that we're getting. That one's kind of cool. So there's the idea. Okay, now the next video, let me pull it up. So the next video here is the same exact idea. It just is showing a much higher quality video of the tubes itself. So here is the screen share, full screen. And I will back it up a little bit to here. I'm not sure what element this is. I'd have to probably turn on the sound, and I don't particularly want to do that because it gets complicated. But here we go. That's what the element looks like. You can kind of see it flickering there on the bottom. And then do the thing. There we go. And then he puts the diffraction gradient over it, and you can see it split into its different color striping bands. So that's cool. Here's another one. I think this one, I don't remember. I used to know all the names of these ones and what colors they would produce. There's some more colors. Shoo-la-la. He's got his hand in front. So this video is just cooler. I think it shows a little bit easier the striping, but it does cut out some of the striping patterns. So there's one of those videos. The tube has to be plugged into electricity because for emission to happen, absorption must have occurred first. You can't have an electron falling unless it was first pushed up into a higher ring. So in the notes, energy came in, and we don't care about that. It happened, and that's great. We're only caring about the energy coming out. But without energy going in, the whole thing doesn't work. So on the one hand, we don't really care about this for our maths and stuff, but conceptually, it's important that the energy came in before it could be absorbed and released. So they have to plug in the gas tubes into an outlet or an electric source so that it can get the energy to move the electrons up, and who cares? And when they come down, that's what we're seeing. But, what if? What if? Instead of plugging it into an outlet, what if we just lit it on fire? And that's what we do all the time. Well, at least I do as a chemistry teacher. So let me show you some videos of, instead of taking the element, putting it in a tube and electrocuting it, what if we take the element and throw it in a fire? So here's a YouTube video, screen share. And this is more like a laboratory one. They are going through and they're showing all of the different salts that they are pouring into the container. We've got lithium chloride, strontium chloride, what is that? I don't know, copper sulfate, etc. And they put all of the different elements and compounds. They've got lead nitrate, potassium chloride, and this is methanol. It is similar to ethanol that you drink, but this stuff makes you blind instead of drunk. So both are very flammable though. So we poured it onto the compounds and it dissolved into the methanol and it's burning off. So instead of getting its energy from, hi baby, love you. Instead of getting energy from like a power source, it's instead getting its energy from the actual fire flames itself. So there's a cool video. Let's see, I think if I scroll forward, maybe. There we go. Here's the final one where it's showing all the different. Hello, I'm trying to teach class. You wouldn't do this if I was normal teaching class. Love you. So there you go. There were all the labels for which elements were used. Once I'm back in the classroom, we will do an experiment similar to that, except for they don't recommend us using methanol anymore for various reasons. So what we do instead is something similar like this, where we use a Bunsen burner. Archie, don't play in the trash can. We use a Bunsen burner / flamethrower and popsicle sticks instead to see the different colors. So she does it kind of boring style, but it's actually really fun when we do it. You can see the different colors. You'll get red and green and purple, just like in the other video, but it is a little bit more controlled of an experiment. So I actually have some pictures on my phone. Let me get the camera ready, of the lab that we do and how much cooler it looks when we do it. So here are a few pictures of students last year. Here's like a really red flame, a green one, another red one. That one's magical. Ooh, focus on that. So that one's all sorts of fun. And then here's a video I have from, let's see, from over the summer. And you can buy these like little pouches at Walmart, usually during the summer. And what they are, ooh, the lights are off. And what they are is just this little metal pouch, and it has all of the different salts and compounds in them. You throw it in your campfire and you can make the campfire like rainbow. So same idea as the chemistry lab, just mixing them all together.